Liquid steel enters this mold at 1,600 degrees Celsius, 2,912 degrees Fahrenheit, hotter than volcanic lava. This is the first step in how modern steel beams are made inside a continuous casting line. The shell forms just 8 to 12 millimeters thick, and if it sticks for even a moment, the entire strand tears. Here's how the beam survives the line. Steel beams look solid, but their structure is born while the core is still liquid. Every minute, molten metal moves from ladle to tundish to mold to rollers to straighteners to reheaters to roughers to finishing mills. One drift in level, temperature, or withdrawal force, and the beam fails before rolling ever begins. If the flow entering the mold is unstable, the shell never forms evenly. The ladle releases steel through a slide gate into the tundish, a buffer that stabilizes flow and removes inclusions. Level sensors track steel height within plus or minus 2 millimeters. If turbulence rises, slag rolls into the stream, embedding defects inside the beam. The mold must cool and move at the same time, or the steel freezes in place. The copper mold cools the outer layer instantly, forming an 8 to 12 millimeter shell. It oscillates 20 to 40 cycles per minute to prevent sticking. Lubrication powder melts on contact, forming a glassy film that keeps steel from welding to the walls. Since the 1950s, curved casters replaced ingot molds, cutting defects by over 70% and enabling continuous withdrawal control. If shell thickness drops below 8 millimeters, it tears. Above 12 millimeters, steel freezes to the mold. The strand leaves the mold while the core is still liquid. Rollers pull the billet downward as sprays cool the surface. Withdrawal speed sinks with solidification rate. If force rises even 5%, the shell tears. Inside, the core is still liquid. Spray zones hold temperature drop in a narrow window. Uneven cooling bends the billet and traps stress. Straightening must happen while the metal is still deformable, but not too soft. Rollers bend the billet from curved to straight. Alignment tolerance, plus or minus 2 millimeters twist. If straightening happens too early, the shell cracks. If too late, solid sections resist bending and internal fractures appear. Before rolling, the billet must heat evenly or deformation concentrates in weak zones. Billets enter a reheating furnace at roughly 1,150 to 1,250 degrees Celsius, 2,102 to 2,282 degrees Fahrenheit. This ensures grain boundaries can flow under force. If temperature drops below 1,150 degrees Celsius, 2,102 degrees Fahrenheit, grain boundaries harden and cracks appear in the next pass. Temperature is tracked across zones. Burners adjust fuel flow every few seconds. The billet is still massive. Roughing distributes mass before precision rolling. Roughers reduce the section and shape it toward an I-beam profile. Roll gap corrections happen within milliseconds. If the web cools faster than the flanges, deformation shifts sideways, creating twist. Here, geometry is set for good: flanges, web, and thickness. Vertical and horizontal rolls shape both web and flanges at once. Laser gauges track flange width within plus or minus 0.3 millimeters and web thickness within plus or minus 0.2 millimeters. So far, Chemistry is stable, the shell held 8 to 12 millimeters, and withdrawal kept the billet intact. If width drifts more than plus or minus 0.3 millimeters, the beam fails dimensional tolerance and cannot pass structural certification. Final strength depends on how the beam cools, not just how it was rolled. Beams cool from approximately 900 degrees Celsius, 1,652 degrees Fahrenheit, down to ambient over 20 to 30 minutes. Cooling must remain symmetric. If cooling rate varies across flanges, beams twist by several millimeters. Roller lifts move beams sideways to balance exposure. Thermal cameras monitor cooling uniformity across length and flanges. Continuous casting survives because of its sensor grid. Thermocouples monitor mold temperature at 100 to 200 Hertz. Powder feed systems correct lubrication flow 10 times per second. Withdrawal load sensors adjust roller pressure every 50 milliseconds. Spray zones pulse water in tight temperature windows, synchronized to billet speed. Even the oscillation waveform is corrected live to maintain powder melt rate. This closed-loop system, temperature, pressure, lubrication, and speed, keeps the shell intact while the core remains liquid. From 1,600 degrees Celsius molten steel, 2,912 degrees Fahrenheit, to a precisely cooled beam, every meter of structure depends on thermal symmetry, controlled cooling, and a shell just millimeters thick. That's how continuous casting and rolling turn liquid metal into the beams holding the modern world. If you want the forging version, where beams are shaped under 40,000 tons of force, tell me which process to break down next.